Okay, so welcome back. Before we start, uh, before we start talking about integration techniques, we do have to pause and talk about a few functions you may not have seen before in calculus. You may not have seen them ever, and those are called hyperbolic functions. Um, and the functions are the cosh of t, called the hyperbolic cosine, or the abbreviation we use is cosh of t, and the SINH of t, the hyperbolic sine, which we call the sinh, since it looks like the word cinch, except you're missing the C, and the hyperbolic tangent. So basically, when you take one of the trig function names and put an h after it, it becomes a hyperbolic one. And the tangent we refer to as tanh as an abbreviation. We also have hyperbolic cotangent, coth, hyperbolic cosecant, cosesh, and hyperbolic secant, sech, S-E-C-H. But we'll mostly focus on these three. And we can see these come up in integrals and also in derivatives as well as we move on here. Now, these functions come about, they're called hyperbolic because they get their definition from the unit hyperbola, hyperbola, get it right. And that's this shape right here, x squared minus y squared equals 1. And so that is the unit hyperbola. So it's centered at the origin. Okay. And very much like your trig functions get their definition from the unit circle, right? The sine and cosine are points on the unit circle. Well, it turns out that the hyperbolic sine and hyperbolic cosine are points on this unit hyperbola, or rather this side of the unit hyperbola. Okay. So points over here that are related actually by, if I remember correctly, it's actually related by the area of this region here. If I remember correctly, that's your T. But those points are called the hyperbolic cosine of T and the hyperbolic sine of T. Okay, so very similar to how your points on for the sine and cosine, the unit circle, are referred to as the sine of t and the cosine of t. So they're defined in a similar fashion. Okay, and it turns out from that definition, since they are points on the hyperbola, then an immediate consequence is that if cosh is the x-coordinate and sinh is the y-coordinate, and they're points on that hyperbola, then they must satisfy this identity. Cosh squared minus sinh squared is equal to 1. And so just like we have that Pythagorean identity, cosine squared plus sine squared equals 1, it's a real big identity for our trig functions. Well, This is a real big identity for our hyperbolic functions. So it becomes a real big deal. And now it turns out the equations of these things actually involve the exponential function e to the x. So we're not going to go into the detail, but you can derive, it can be shown that based on the definition, which again I've only kind of given you part of it, just to give you the idea that it's a point on the hyperbola, then it turns out that the hyperbolic cosine is e to the t plus e to the minus t all over 2. And it turns out the hyperbolic sine of t is e to the t minus e to the minus t all over 2. And so if you resort to looking at their graphs, you can graph those on Desmos. Just have to locate them. So there they are, cosh x. And you'll see that the graph of cosine looks an awful lot like the graph of x squared. Although if you compare them, x squared a little bit sharper at the bottom. Even if we did x squared plus 1, you can see it's sharper along the bottom than the cosh. And then the other one, the hyperbolic sine, looks an awful lot like a third degree equation, right? It's very similar, looks very similar to the x cubed graph, right? Again, the x cubed graph though being sharper. Okay. So very similar type of graph. Okay. So those are the two graphs, the hyperbolic cosine and the hyperbolic sine. Of course, you could graph your other hyperbolic functions as well. You just have to, choose them when you graph it. All right, they're all there. You can, if you want to, you can look at the graphs of the other hyperbolic functions there. Hyperbolic sine, cosine, tangent, cosecant, hyperbolic cosesh, sesh, and coth. Just wanted to take a quick, brief look at those. And you can actually show these results, using your rules for derivatives. It turns out that when you differentiate the hyperbolic cosine, you actually get the hyperbolic sine. In other words, the derivative of this function is actually going to be this function. And it turns out that the derivative of the hyperbolic sine is the hyperbolic cosine. Okay. So using those two facts here, I'm going to show you what the derivative of the hyperbolic tangent is. So again, you can verify these just by using your derivative rules here for cosh to see that its derivative is in fact the hyperbolic sine. And likewise, the derivative of the hyperbolic sine is in fact the hyperbolic cosine. But let's use those two results to figure out the hyperbolic tangent of x, what its derivative would be. Well, a hyperbolic tangent is just defined the same way that the regular tangent is. It is the hyperbolic sine, and I'm doing x here, not t, so let me make sure I fix my variables on the dt here. That should be dx instead of dt. So hyperbolic sine of x over hyperbolic cosine of x. So by the quotient rule, that's the bottom. Hyperbolic cosine times the derivative of hyperbolic sine, which would be hyperbolic cosine, minus the top, hyperbolic sine, times the derivative of the bottom. Derivative of hyperbolic cosine is hyperbolic sine. Right, and then all that is over hyperbolic cosine squared. So this is just going to be hyperbolic cosine, or cos squared, minus sinh squared, all over cos squared. But cos squared minus sinh squared is 1. So it's 1 over cos squared. But cos, 1 over cos, is the hyperbolic secant. So this is the hyperbolic secant squared. Okay. And in a similar fashion, you can find the derivatives for the other 3 hyperbolic functions as well by using that, by using these 2 rules along with your primary rule here, that cos squared minus sinh squared is 1. Okay. So this is just kind of a little introduction to the hyperbolic functions. We'll see them come up occasionally in some problems that we're dealing with, so we do want to be aware of them, but it's not something we're going to worry a whole lot about. Okay, but we will see them, and they could come up with some problems here or there. So that's why I wanted to take some time and introduce you to them. And again, their definition is very similar to the definition for the unit circle, in that it's related to some value that leads you to a point on the graph of x squared minus y squared equals 1, just like the trig functions are based off of a graph that leads you to points on the circle x squared plus y squared equals 1.